For some reason, I did seem to not get homework number 28 into Moodle, which I just handed back homework 29. So if you could look for that after class, right after class, and just bring it up to me after class, that would be good. Your homework 28, but I handed it back in your POs, I think, last Friday or something. What's the most beautiful equation in the universe? Does anybody know? Do you know?
e to the I5 plus 1 equals 0.
You are right. Alyssa is right. That is the most beautiful equation in the universe. Why? Because in one simple equation, it's got the 5 most important numbers in the universe. 0, 1, e, pi, and I being the square root of -1, the imaginary unit. It's got the, I guess you could say, 3 most important operations in the universe as well. Addition, multiplication, and exponentiation. And the most important equivalence relation. What's our favorite equivalence relation? Equals. There we go. All in one simple equation. Isn't that amazing? Anybody else a physics major? You're like a physics major, aren't you? And you knew the right answer even. I mean, any other, sometimes physics majors might, I didn't know that, I didn't mean that as a bad thing. I meant that as physicists might sometimes say, well, C or H bar is more important. You know what those are? You know what those are, right? C is the speed of light. H bar is called Planck's constant divided by 2 pi or something like that. Really important physical constants, but physical constants are not numbers. Did you know that? Physical constants are not numbers. Because their values depend on the units that you use. Meters, seconds, etc. So these are the 5 most important pure numbers in the universe, okay? And I always say if you're ever abducted by aliens and they say, we'll let you go if you tell us the most beautiful equation in the universe, they'll let you go. Just let them know. They know, okay? Why is it true though? Well, it's actually a special case of a more general fact, which you might say itself, some people might argue is more beautiful perhaps, but I mean, yeah, in some ways, but I'm saying this is the most beautiful equation. E to the I theta equals cos theta plus I sine theta. I suppose you could argue these are essentially the same thing, so they're both the most beautiful equations. This is called Euler's identity. This one's going to follow from this one by plugging in theta equals pi and doing a little rearranging, right? Because cosine of pi would be -1, sine of pi would be 0, you'd get e to the I pi equals -1, then add 1 to both sides, e to the I pi plus 1 equals 0. But why is this true? Well, I will give you the argument based on series. It may not be fully satisfying because it might feel like cheating perhaps, but there are other good reasons why this is true, other ways you could argue why this is true besides series. So we know the Taylor series for cosine, sine, and e to the x. Cosine of x being 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. Sine of x being x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. E to the x being 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. And right away you do see, I mean, there's got to be some sort of connection between e to the x and cosine and sine, because you can combine the series for cosine and sine, get rid of the negative signs, and you get the series for e to the x. Can you replace x with complex numbers involving the imaginary unit I? It turns out you can. I'm not proving that right now. That's for topics in math in the spring, right? Complex analysis.
Yes.
prove that. That's okay to do. But for the moment, let's just go ahead and make that replacement. E to the I theta, replace all those x's with I theta. 1 plus I theta plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the 4th over 4 factorial. Let's go a couple more here. I theta to the 5th over 5 factorial. I theta to the 6th over 6 factorial, etc. Alyssa, what's I squared?
Negative 1.
Negative 1. I squared is negative 1. That third term simplifies to minus theta squared over 2 factorial. Minus. Look at that. If I squared is negative 1, what's I cubed? Somebody else. Negative I, yeah. I times negative 1, negative I. This I cubed becomes a negative I. Negative. Almost like magic. What's I to the 4th? I cubed is negative I, and I squared is negative 1. I to the 4th is I times, wait, I lost myself here. What we, I cubed is negative I times another I gives you 1. This simplifies to theta to the 4th over 4 factorial. If I to the 4th is 1, what's I to the 5th? I. Algebraic structures. That forms a cyclic group of order 4. Oh. He said the dreaded cyclic group word. Actually, no, cyclic groups are really simple, right? You remember that? Cyclic groups are nice.
It's not as dreaded as just Cauchy, but...
Cauchy!
Oh, sorry.
That just hurts my ears. Theta to the 6th is the same as, or I to the 6th is the same as I squared, negative 1, etc. Can we just rearrange these terms? Yes, because this is absolutely convergent. Hey, an application of absolute convergence. Although this is still a little fishy because in rearranging the terms, I've got the sum of 2 infinite sums. All the even powers of theta together, dot, dot, dot. Can I do this? Is this allowed? Can I have dot, 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 and then a plus there? Oh, boy. The other terms I can factor out an I. There we go. Cos theta plus I sine theta. Can you do that? Well, it turns out you can. This not only converges for all I times, not for all theta, it's absolutely convergent, each of these series. And you can do this even though you've got infinitely many terms here. And then another plus, so just think of each of these things separately, essentially. And being multiply this one by I and add. These are separate series that converge into 2 things. Turns out this is okay. It's even more beautiful to try to visualize this. Let's come over to Mathematica here on the screen. Complex numbers, complex analysis is definitely one of the most beautiful subjects in math. In fact, that's going to be one of our main themes when we do that in the spring. And you can illustrate this identity, Euler's identity, in the following way. What we have here is a picture of something called the complex plane. There's a real axis corresponding to the real number line, and there's an imaginary axis. It is there though, it's not just in your imagination. It's there on the screen. It's just a label, okay? Real numbers are on the real axis. Excuse me, for example, the number 3 is right there. Number -1 is right there. Numbers on this imaginary axis are pure real multiples of I, the imaginary unit, square root of -1. The 1 there corresponds to the complex number I. 2 corresponds to 2I. That's 1.5I right there. Down here is -I. These are points in the complex plane. An arbitrary point, say right there, corresponds to the complex number with real part 2 and imaginary part 1, meaning it's the complex number 2 plus I. Does that make sense? Corresponding to the point with coordinates 2 plus 1. Point down right there would be 3 minus I. This is the unit circle, right there, that black circle, in the complex plane. What do we have here? We've got theta. What is theta? Theta is a real number. Its value on the real axis, actually, the dot there is not the value of theta. I think this dot here is the value of e to the theta. And we've got this other dot on the unit circle here. That's a dot with coordinates, rectangular coordinates, cosine theta, comma sine theta. I've got a step, I've got an R. R just affects the scale here. What's the step going to do? The step is going to add one more term in the partial sum up here. That's the series for e to the x, a partial sum for the series for e to the x. So I think what I've got here so far with this red line and this two blue lines, this red line represents the number 1. This blue line represents the number theta. 1 plus theta is the first 2 terms in the series for e to the x, replacing x with theta. The other blue line that goes straight upward represents I times theta, real multiple of I. Let's step up 1, come back to the screen. Here I go, I'm going to click the step forward. See what happened there? Do it again. Two red lines get added to the picture right now. This first red line here represents the value of theta squared over 2 factorial as a real number. The second one is negative theta squared over 2 factorial as a real number. It's going to the left because it's a real number. In this expansion, it's this. Negative numbers can be thought of as going to the left if you're thinking of these numbers as being vectors, essentially, even though I didn't draw arrows. If I add more steps here, you're not going to see much more because, yeah, the black dots are covering it. But if I go back and now I change theta, make theta bigger, we can see what's going to go on here a little bit more clearly. Okay, so theta is about 2.28 here. This is the real value of e to the 2.28, close to 10. The red line there is the number 1, essentially as a vector. The blue line there is theta. 2.28, is that about 2.28 away from 1? Yes, it is. That's at about 3.28. This blue line is I times theta, just like before. It's got to go up. because it's a multiple of I. Now watch the steps. This is theta squared over 2 factorial. Theta squared over 2. 2.28 squared over 2. This is negative theta squared over 2 going to the left. Add the next term. Now we can see it. Logic. Here we go. That's theta cubed over 3 factorial. Theta cubed over 6 as a vector pointing to the right. Value close to 2. Coming from that term with theta in place of x. And the other blue one coming back over here is like a vector pointing downward. That's I times theta cubed over 3 factorial. I cubed, excuse me, which is negative I. Negative I times theta cubed over 3 factorial. We're going down there. And as we continue stepping forward, we continue adding more terms in both series. And we can see in both cases this group of lines converging to that dot, which is a real value of e to the theta. And this group of lines converging to e to the I theta, which is cos theta plus I sine theta, which is on the unit circle. As it has to be, because its real part is cos theta and its imaginary part is sine theta, and cos squared theta plus sine squared theta equals 1. And that's going to happen no matter what theta is. You can geometrically visualize why this point is on the unit circle. It's not a proof, of course, but you can understand what's going on with these partial sums when you replace x with I times theta. So this is supposed to help you believe that's true, essentially, with a nice visual. It's not a proof, of course, but it helps you believe it. Is that beautiful, don't you think? I think so. All right, for the rest of the day today, we are going to continue just focusing on calculations today. Essentially, this will be like a Calc 2 lecture. Okay, so that's good, I suppose. Focus on calculations you should be able to do and things you should be able to find for the exam. On Wednesday, we will review for the exam, but we'll also talk about proofs that you should be able to do. I do hope to spend the last 5 minutes also addressing a couple issues with the homework, not just the homework I handed back today, but also with the one I handed back last Friday. Try to remember to do that about 8:45 or so here. Well, I probably should have kept the series for e to the x out, but let me go ahead and write it as a summation. Here's the series for e to the x as a summation. You should know this. Again, there's no calculator or no card for our exams, although there will be partially for the final exam. There will be a closed book portion and an open book portion for the final exam. But here for the midterms, there's nothing you can use. So you need to memorize this, either in the summation form or the long form without the summation sign. What's something you should be able to do with this? You should be able to confirm that this converges for all x, for example. How do you do that? You got factorials involved. Remember I said with factorials the best test to use is? Ratio test, chapter 6 actually. Think of x as fixed here. You ultimately think of x as a variable, but when you're thinking about where this converges, think of x as fixed. You've got factorials involved, the best test to use is the ratio test, and to hope that it works. And to hope that you can also just calculate it as an ordinary limit and not a lim super or lim inf. And they will, for examples like this, the limit will be fine. The lim sup and lim inf only come up in those strange examples where the AKs are piecewise defined or having -1 to the k power involved in a funny way. Let's see what the ratio test shows about this. You are going to need to keep the absolute value signs in there around the x's, because x could be negative. This is the AK. terms of the series that you're adding up. Let me go ahead and jump to this quotient as a product right away. That's okay for you to do as well. Replace k with k plus 1 first. Multiply by the reciprocal of ak. So you get a k factorial divided by x to the k. You can put absolute value signs around the whole thing as well. I could do that back here too. The quotient of two absolute values is the same as the quotient as the absolute value of the quotient. And it's pretty nice here. You get nice cancellation. K plus 1 factorial is k plus 1 times k factorial. So the k factorials cancel, leaving you with k plus 1 there. X to the k's cancel, except one of those x's there. The x no longer involves a k. You could factor it in front of the limit sign if you like. K plus 1 is positive. You no longer need the absolute value signs. You do need it around the x though, in general. Here it doesn't matter, but in general you do. This limit is 0. You get 0, which is less than 1, and here's the key point, no matter what x is. The value of x is irrelevant for this limit equaling 0. Therefore, by the ratio test, this series converges no matter what x is. X could be a googolplex, it doesn't matter. This still converges. The factorials grow big so fast that it still makes this thing converge. If x were a googolplex, then it's, you know, an unimaginably large number for e to the x, but it still converges. Googolplex is that number there, a 1 with a Google zeros after it, where Google is a 1 with 100 zeros after it. I want to think about a really big number here. What about if you had a googolplex factorials after it? Oh, it's still finite though. That boggles your mind, doesn't it? People don't know how long eternity is. Forever. Imagine living that many years and more. What else? I wrote down the series for cosine and sine. You should know those. You should know them in their summation form, and it's a little tricky in summation form. If you're letting k go up by 1, you want the powers of x to go up by 2 each time. You also want the signs to change, plus, minus, to alternate. Starting with a plus, it's good enough to do a k plus 1 there. Cosine has only even powers, starting with x to the 0. You want 2 k's here, like that, if you write it in summation form. And it's this form that you'd want to use if you were going to apply the ratio test to show this converges for all x. By the way, should have mentioned this a few minutes ago, just because I've shown this converges for all x does not mean it equals e to the x. That takes more proof. That takes a theorem in section 7.5, which I haven't talked about yet. An error-bound theorem to prove equality here. Just because this proves this converges for all x does not mean it equals e to the x. That's a different issue, a harder issue to deal with. Same thing here. You can use the ratio test with it in this form to show this converges for all x. The interval of convergence, so to speak, is the entire real number line. But that doesn't mean it equals the cosine of x, though it does. That takes that theorem that I'm hinting at section 7.5. Maybe go ahead and say the number of the theorem in just a second, and then I'll answer your question. The number of the theorem I'm talking about is theorem 7.21, actually. Yeah, 7.21 is the one that does it. Question?
Isn't that first term, wouldn't that be a negative? Because it's K plus 1 is just 1.
Yeah, you're right. Thank you. Thanks. Sine of x, if you start at k equals 0, you'd also want a k there. You want odd powers of x starting with the first power. So if k starts at 0, you've got to use 2k plus 1. Okay, you should know those. You should also know how to use those for other kinds of calculations. For example, to find the series for x squared sine of x cubed. All you have to do is take the series for sine of x and replace all the x's with x cubed. And then multiply times x squared at the end. This is not as hard as it sounds. You do not have to use the generic Taylor series formula involving the kth derivative of f evaluated at the center of the interval of convergence. Just take the series for sine of x and replace all the x's with x cubes. And then multiply by x squared. Thanks. So you'll get x to the 5th minus x cubed cubed is x to the 9th times x squared is x to the 11th. X cubed to the 5th is x to the 15th times x squared is x to the 17th. Looks like the power of x keeps going up by 6. The next one should be x to the 23rd over 7 factorial, then x to the 29th over 9 factorial, etc. What would the interval of convergence be in this case? For what x's does this converge? Take a guess. What would be the most logical thing?
All of them?
For all x, yeah. The series for sine of x converges for all x. X is just an arbitrary real number. X cubed could be thought of as an arbitrary real number as well. This got to converge no matter what x cubed is. You multiply by x squared, it doesn't affect convergence. The interval of convergence is the entire real number line. The radius of convergence, so to speak, you've read about this probably, is infinity. We'll do examples where the interval is not the entire real number line. Travis?
So is there going to be stuff that we haven't talked about in class that'll be on the test that we were supposed to read about? Because there's quite a bit that...
Yeah, there's a lot that
we haven't
there's a lot of
covered.
theorems, and proofs that I haven't talked about yet. You should, for the moment, read them and study them. We'll talk about what to know about those on Wednesday. Okay? You can check, I do want you to be able to do these series calculations, okay? So this is calculus 2 stuff, but I think it's worth doing again in real analysis because it's easy to forget. I don't want you to forget it now and in the future. You can check these things on Mathematica in the following way. For example, with this one, the syntax here is series will calculate a Taylor series for whatever function is inside here before the comma. Here you're emphasizing x is the variable. You're emphasizing the center of the interval is 0. So in the general Taylor series formula, you're plugging in 0 into the derivatives. And up through the 29th degree term here, which is not that many terms here because you already wrote it on the board. There we go, and yep, that matches what we have on the board. Here we have big O of x to the 30th. That's just saying all the other terms are degree 30 and higher. So that checks out. You can check your answers. You should also know the fundamental fact that this equals this. Why? You should be able to say why here. It's a geometric series over there with a leading term being 1 and r common ratio being x. It's got to converge to a over 1 minus x, a over 1 minus r. As long as the absolute value of r is less than 1, x is between -1 and 1 strictly. That's a pretty fundamental fact because you can use it to derive a lot of other facts. I'm going to go fast and furious through these other facts. If you want to know the Taylor series for this one with a plus x instead of a minus x, well, just think of it like this. And then go back up here and replace all the x's with negative x. X, again, is after all just a symbol. It just represents an arbitrary number. Negative x can be thought of as representing an arbitrary number as well. And you quickly get the Taylor series for this one centered at 0. And these are going to be the Taylor series too, by the way. They're not just valid series expansions. They will be the same thing you would get if you used the general Taylor series formula. This one's a good one to do. Just replace all the x's with negative x squared. And since this one was true when the absolute value of x was less than 1, this one's going to be true when the absolute value of negative x is less than 1, which of course, I hope you know, is equivalent to the x itself having an absolute value of less than 1. This one's going to be true when the absolute value of negative x squared is less than 1, which is also equivalent to x itself having an absolute value less than 1. So in all three of these cases, the interval of convergence is the open interval from -1 to 1, not including the endpoints. The center of the interval, the midpoint, is 0. That would be, if you're trying to find the Taylor series for this using the Taylor series formula, again involving the kth derivative evaluated at a, the a is 0 in all these examples. You're centering this interval at 0. The radius of convergence is the distance between the center and either endpoint. That is 1. In complex analysis, by the way, this will become a literal radius of a literal circle in the complex plane. So that's another good reason to call it a radius. Actually, better to call it a disk of convergence in the complex plane when we do complex analysis. But the same expansion is still true where x is a complex number, it turns out. These are some of the most important ones to do because it's also useful to, like, for example, integrate these to find other series. Integrate them term by term, where I'm really using an important theoretical fact in section 7.3, the inherited properties. Talk about when you've got uniform convergence of a sequence of functions. The limit of their integrals is what you would expect. And with series, it turns out you can integrate term by term when you have uniform convergence. When do you have uniform convergence in these cases? I'm going to talk about that in a few minutes. But for the moment, let's just go ahead and integrate these term by term. For example, what happens if we integrate, let's do this one actually. This one term by term. It is valid to do, I'm just telling you. It is valid to integrate this term by term, to integrate each of the terms in the infinite sum individually and add up the results. Let's put the constant integration in front, c, and then integrate 1 and get x. Integrate negative x, get negative x squared over 2. Integrate x squared, get x cubed over 3. Integrate negative x cubed to get x to the 4th over 4 minus, etc. What does this integral equal? Well, it's the natural log of 1 plus x. You could say the absolute value of 1 plus x in general, though I'm not going to bother with that. We're only going to consider x to be bigger than negative 1 here. So that x plus 1 is bigger than 0. So I'm not going to worry about the absolute value signs. This affects what c is. If I want to get an expansion for natural log of 1 plus x, I better choose c correctly. Natural log of 1, plug in x equals 0, is 0. When I plug in x equals 0 on the left side, I get 0, because natural log of 1 is 0. You plug in x equals 0 over here, you get c. Therefore, c must be 0. The fact that natural log of 1 is 0 implies c is 0. So what we have here, evidently, is an expansion for natural log of 1 plus x as x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, etc. Does this also converge on this interval? Actually, no, though almost. It does converge for all such x, but it actually converges at one more value of x, one more point. What other point would get added for the convergence of this series here?
Equals 1.
Yeah, if x is 1, you get the alternating harmonic series, which does converge by the alternating series test, though not absolutely. The interval of convergence is this interval. That's where the series converges. You can use the ratio test on the open interval from -1 to 1 to verify convergence. As far as when x equals 1, it's the alternating harmonic series, which we know converges by the alternating series test. It does not converge at -1, because if you replace x with -1, you get the negative of the harmonic series, which would diverge. So you add one more point of convergence when you integrate here. It's not real significant. It's significant enough to say it's true, but that still doesn't prove this equals natural log of 1 plus x, though it does. For these values of x, including at 1, which explains why the sum of the alternating harmonic series was natural log of 2. I think we saw that before. Log 2 means natural log of 2 in Mathematica. I think we saw that before. I'm getting this class and my Calc 2 class mixed up because we're doing the same kind of topics here. But I think I showed this before. The alternating harmonic series sums the natural log of 2. Though the convergence is very slow, because it's not absolute convergence. What about uniform convergence and being able to integrate term by term like this? It turns out you can integrate term by term in the interior of the interval of convergence. If it's an open interval already, by interior I mean the open interval itself. You don't get uniform convergence over this entire interval. The graph of this function's got a vertical asymptote, -1. However, you do get uniform convergence on any proper subinterval, which does not include the endpoints. And that turns out to be good enough to prove that you can integrate term by term by the theorems in section 7.3, which we're not talking about today. We're saving for Wednesday. What would happen if I integrate this one term by term? Integral of 1 over 1 plus x squared. That should be like a gateway kind of problem. It equals what?
Arctangent.
Arctangent. if you integrate this one by term, in a similar kind of way, you've got the c there, and you use the fact that arctangent of 0 is 0. Turns out the c would be 0 then. And you can ultimately say that arctangent of x, I'm going to integrate this term by term in my head without writing it out there as an integral. Integral of 1 is x, integral of negative x squared is negative x cubed over 3. Integral of this one's going to be positive x to the 5th over 5, etc. What's the interval of convergence for this? Turns out this also converges at 1, but not negative 1. And an interesting thing happens when you replace x with 1 here. Arctangent of 1 is pi over 4. And so what you get when you replace x with 1 is an expansion for pi over 4, which, if you multiply both sides by 4, gives you an expansion for pi. Cool. Pi equals this infinite series. And you could use that to approximate pi, though I would warn you the convergence is very slow. And it takes many, many terms to even get 3.14, I think. There are plenty of faster converging series related to pi that give you faster ways to approximate pi more quickly. That could be a topics in, not a topics in math, but a foundations of math paper in January related to finding all the formulas for pi that you can related to pi. There are hundreds or even thousands of them that allow you to write pi as infinite series or even infinite products. It's another thing you can look into, what are infinite products. Well, I will tell you, if you do that for foundations of math, you'll be doing complex analysis before topics in math. But it's still doable if you really want to do it. You can also differentiate term by term. It's another theorem. Under certain conditions. And it turns out that on the interval of convergence for these things, it can be done. What would happen, for example, if you differentiated this one term by term? You get the derivative of 1 over 1 minus x, which is the same as 1 minus x to the negative 1 power, is the derivative of all this. And it is valid to do it term by term. Do that. But what is this? This is the same as negative 1 minus x to the negative 2 power times negative 1. It's the same as 1 over 1 minus x squared, which is the same as our original function squared, which hints at yet another way to find the series for this. Take the series for this and square it. I'm going faster, I hope you're following me. This is an expansion, and the pattern does continue. You get plus 4x cubed plus 5x to the 4th, etc. The coefficient keeps going up by 1. That's an expansion for this function, which is the same as that function. But this function is the square of this function as well. If I square this infinite series, I should get the same answer. Are you kidding? Square an infinite series? No, I'm not kidding. Let's square it. Multiply it times itself. How do you do such a thing? Without proof, here's the method. Take the first term over here, 1, multiply it by every term over there once. Write out what you get. Now go to the second term over here, x. Multiply it times every term over there once. Write out what you get. And put like terms underneath the previous term. So x times 1 is x. Put it under the previous x. X times x is x squared. Put it under the previous x squared. X times x squared is x cubed. Put it under the previous x cubed. Go to the third term here, x squared. Multiply it times every term over there. X squared times 1 is x squared. Put it under the other x squareds. I hope you see where this is going. X squared times x is x cubed. Put it under the other x cubed. Next term there is x cubed. X cubed times 1 is x cubed. Put it under the other 3x cubes, etc. What we have here is an infinite sum of infinite sums. Boy, that sounds fishy. Turns out to be okay in this case. And if you add the like terms, lo and behold, you do get the same answer. What's the interval of convergence? It turns out to be the same intervals before. You can lose endpoints when you differentiate term by term. For example, if we take these series for arctangent of x or natural log of 1 plus x and differentiate term by term to get those other series that we integrated, then we lose convergence at x equals 1. So you can gain endpoints as possibilities where things converge when you integrate, but you can lose them when you differentiate. One more quick kind of example. Boy, I don't have time here. Okay, I'm going to go through this example pretty quickly. It is very tricky, what I'm about to do. If I remember correctly, I think the book does do an example. What if you had a function like this, and you wanted to expand this in a series, centered somewhere other than 0, say, like maybe centered at 6, just to pick something, centered at a equals 6. How in the world would you do that? Through some tricky algebra to relate it to the sum of a geometric series. That's the overarching goal here, is to make it look like that. And then use a formula for geometric series. And if you're going to center it at 6, you want the R to involve x minus 6. That's the other thing to focus on here. So how can that be done? Well, you could go ahead and just replace the x here with x minus 6. But of course, there's a price to be paid if you do that, if you want equality here. By replacing x with x minus 6, I really ended up subtracting 18 from the bottom. So to compensate, I have to add 18 back in. I'd like there to be a minus sign there. I'd like there to also be a 1 there. Let's focus on making that a 1 there. How do you make that a 1? Well, just make it a 1. How? Factor out 25, that's how. But of course, there's a price to be paid. If you factor out 25, you got to put an over 25 there. And then, yeah, I would like a minus sign there, but that's easy to fix. Let me bring the 25 up top. 5 divided by 25 is 1/5. Write it like this. Now I have it in the form a over 1 minus r. A is 1/5. R is this crazy thing, negative 3 times x minus 6 over 25. I can now use the formula for geometric series in general to expand this as a series in x minus 6. The Taylor series centered at 6. Let me do that quick. And we'll check it on Mathematica. So I'd have a 1/5 out in front that could be multiplied through. 1/5 would be the first term, minus 3x minus 6 over 125 for the next one, because it's the 1/5. gets multiplied times the 1 over 25. Plus, it'd be 9x minus 6 squared over what? 25 squared is 625 times another 5 because of the 1/5. What, 3,125? Is that right? 625 times 5. That's the first 3 non-zero terms. Let's check it with series. Function is, type it in the original form, 5 over 7 plus 3x. I'm trying to find a series, a Taylor series for it, with x as the variable, centered at 6, not 0. And we're going through degree 2 here. Looks good. So some tricky algebra can get you the answer. I'm saying I do want you to be able to do this. So this is something to practice. You can make up your own examples similar to this. Change these numbers. Change what A is, where you're centering the series at. Try to do this. What's the interval of convergence? R, the common ratio has to be less than 1 in absolute value. R, again, is negative 3 times x minus 6 over 25. That's got to be less than 1 in absolute value. That is equivalent to the distance between x and 6 being less than 25 thirds. 8 and 1/3. The radius of convergence is 25 thirds. The interval goes from 6 minus 25 thirds to 6 plus 25 thirds, not including the endpoints. I want the common ratio to have an absolute value less than 1. You can write that in this way. It's a simpler way to think about it. I wanted to address some more problems. I guess we do have a few minutes here. And the homework that I just handed back, one of the problems that I did grade gave people more trouble than I imagined it would. Problem number 6, section 6.1. Trying to show that if you've got two sequences of functions, fn and gn, that both converge pointwise to f and g, to show that the sequence of formed by adding these things together converges to f plus g, converges pointwise. One big mistake that about 5 of you made was you were dealing with summations, and I have no idea why you had summations in there, because this is sequences, not series. There's no summations in the problem. And another problem that another 4 or 5 of you had was that you weren't focused on what pointwise convergence really means. It means for each fixed individual x in the interval, the fact that this converges pointwise to this means this sequence of numbers converges to this number. And this sequence of numbers converges to this number for any given x. And then you'd have to show something similar for this. You'd have to put the x's in there. For any fixed x, show this converges to that. And it's just theorem 2.7 in chapter 2. Some of you quoted that theorem, but you weren't really using the theorem in the way you were writing out your proof. The x's, when you use that theorem, have to be there. The fact that x is arbitrary is important to say. Give me an arbitrary x in the interval. To show this sequence without the x's converges to this function without the x's, you've got to show this sequence with the x's converges to this number with the x's for each x. So give me an arbitrary x in the interval, and then just do that. So it really was a pretty easy proof, but only 3 or 4 of you got full credit for it. The other one I wanted to mention was on the preceding assignment, and it was a problem back in chapter 6. It was the problem where you used this fact to show that absolute convergence implies convergence. It's a comparison test. I don't have time to go over that, but it many of you had the basic right idea, but you struggled with saying things correctly. And I guess maybe on Wednesday we'll go over that and then work out on how to say things correctly and that kind of problem, because that could come up in the test.
Do you know what?
It's in section 6.3, it's like number 3 or something. What's your question?
Is there last assignment in our POs? Because I can't find it.
You can't find it?
Yeah.
Yeah, it might be, I think they put it in your POs on Friday.
Oh, okay.
So yeah, if you could get to my office here, I have a meeting in the next hour, but you can put it on my office door.